You know, inside every single jet engine, there's a world of invisible, violent chaos. Air gets compressed, ignited, and just blasted out at unbelievable speeds. Today, we're going to take a journey right into the heart of that storm. We're going to witness a digital battle that is completely redefining how we design the future of flight. Okay, so meet the hero of our story, the high-pressure turbine blade. This thing is an absolute marvel of engineering. It's been sculpted to squeeze every last drop of energy from superheated gas. But here's the catch. The air flowing over its surface isn't some smooth, gentle river. No, it's a turbulent, swirling, chaotic torrent. And designing for that chaos? Well, that's one of the toughest problems in all of engineering. And this is what that chaos looks like, broken down. As air just screams past the back edge of the blade, it creates this swirling pattern of vortices. This shedding process sends out pressure waves that actually travel back upstream, hitting the blade's surface over and over. It's this incredibly complex, violent dance of forces. And if your design can't handle it, you lose efficiency, you lose power, and you lose reliability. Big time. So, how in the world do you design for something you can't even see? Well, you simulate it. For decades, engineers have been using powerful computers to build these digital wind tunnels. But today, we've got 3 different methods. 3 digital competitors, if you will, and they're all stepping into the ring to see which one can truly capture reality. First up, we have RANS. This is the seasoned veteran, the workhorse of the industry for years. The best way to think about it is like a long exposure photograph of a busy street, right? It blurs out all the individual cars and people and just gives you this one single averaged image. It's fast, computationally speaking, and it gives you the general idea, but you lose all of those crucial split-second details. Next in the ring is URANS, kind of the next evolution of the classic model. If we stick with our photo analogy, URANS is more like a time-lapse. It can actually capture the main repeating patterns over time, like the pulsing of traffic lights or the general ebb and flow of cars. It's a definite step up because it sees some of the unsteadiness, like that vortex shedding we talked about, but it's still averaging out and missing all the truly random, chaotic bits of turbulence. And finally, we have the challenger, LES, or Large Eddies Simulation. Now, this is a completely different animal. LES is like bringing a high-speed, slow-motion video camera to the party. It doesn't average things out. Instead, it directly calculates the large, the energetic, the most important turbulent motions, and it only models the tiniest, most predictable little eddies. And the promise here, it's a breathtakingly detailed and accurate picture of reality. And this right here illustrates the core difference perfectly. Look on the left. With RANS and URANS, the simulation has to use a mathematical model for all of the turbulence. It's all a kind of educated guess. But on the right, with LES, the computer directly calculates most of the turbulence, the big, important stuff, and only has to model that tiny little piece at the very end. The takeaway is simple. LES is doing more physics and a lot less guesswork. But, theories and cool analogies are one thing. To find a true champion, you need a real-world test. These simulations aren't just running in a digital vacuum. They're about to be pitted against a physical benchmark, a real proving ground for all their digital predictions. And here it is. This is the actual blade, built for a major European research project. It is covered in hypersensitive pressure sensors that record exactly what's happening on its surface inside a high-speed wind tunnel. This physical experiment, this is our ground truth. This is the hard data that our 3 digital competitors absolutely have to match. And in the digital world, this is the arena. This is the computational mesh. It's a meticulously constructed 3D grid made of hundreds of thousands of points that surround a digital version of the blade. It's inside this grid where the fundamental laws of physics are solved to simulate the flow of air. So, the stage is set. The competitors are ready. The real-world data is waiting. The big question is, which simulation is going to come closest to predicting the chaotic, violent, and intricate reality of the flow around this blade? All right, it is time for the main event. Let's put these simulations side by side and see how their vision of this invisible world stacks up against what we know is actually happening. Okay, so here's the result from RANS, our industry veteran. And yeah, just as we expected, it's a smooth, steady picture. You can see the wake trailing behind the blade, sure, but it's completely averaged out. There are no vortices, no pressure waves. It gets the big picture maybe, but all that vital unsteady physics, it's completely gone. Now let's look at UN trends. And wow, this is a huge improvement. You can clearly see the vortices shedding off the back edge, and you can see those pressure waves moving outwards. But look closely. The structures seem kind of weak, right? Overly dissipative. That means they lose their energy and just fade out way faster than they should. It sees what's happening, but it doesn't quite capture its strength. And now, here is LES. The difference is just stunning. The view is incredibly rich with detail. The vortices are sharp, they're well-defined, and they stick around much farther downstream. The pressure waves are crisp and clear. This looks like a far more complex and energetic reality. This is our high-speed camera in action, and the footage is spectacular. But of course, the ultimate judge is reality itself. This is a high-speed photograph from the actual experiment, capturing changes in air density, and you can see it right there. The chaotic, detailed, energetic flow. When you put them all side by side, well, RANS isn't even in the game. URANS gets the basic idea. But only LES, with its incredible high-fidelity detail, truly begins to capture the complex beauty of the real physics. So let's move from pictures to cold, hard numbers. This graph shows the pressure distribution along the blade's surface. The squares, that's the real-world data from the lab. Now look at the lines. The diamonds and circles, that's RANS and URANS, they miss the mark in some really key areas. But that solid black line representing LES, look at that. It is practically tracing the experimental data. It's an almost perfect match. And here it is. This is the knockout blow. One of the most critical things to get right is the frequency of that vortex shedding. The experimental data is crystal clear on what the answer should be. The URANS simulation, it was off by 26%. And the LES simulation, it was off by a mere 4%. That isn't just a little better. That is a massive, massive leap in accuracy. So after comparing the visuals, the graphs, and the hard data, the results of this simulation showdown are N. And believe me, there is one clear and undisputed champion here. And the winner, by what I can only call a technical knockout, is large eddy simulation. In its ability to capture the complex, unsteady physics that are just so critical to turbine blade performance, LES proved to be in a class all by itself. But every great victory has a story, and this one comes with a pretty crucial trade-off. This incredible, unmatched accuracy, well, it doesn't come for free. It comes at a steep, steep price. So let's actually quantify that price. According to the research, running that baseline RANS simulation took about 30 CPU hours. Not bad, but to get that beautiful, high-fidelity result from LES, that took 950 CPU hours. That's more than 30 times the computing power. So the lesson here is pretty clear. Precision is expensive. So why does all this matter? I mean, why spend all that computer time? Because this level of accuracy, it completely changes the game. It lets engineers design blades that are more fuel efficient, which leads to cleaner airplanes. It helps create more powerful and reliable turbines for generating our electricity. It allows us to stop relying on blurry averages and start designing for reality, turning our computer models into true digital twins of actual physical hardware. And this really leaves us with a fascinating final thought. Today, a 950-hour simulation is a major research project. But we all know that computing power just keeps growing exponentially. As the supercomputers of today become the routine desktops of tomorrow, you have to wonder, what currently impossible engineering challenges will we finally be able to solve?